if, so for those who have not seen Nicoletta or sent emails to Nicoletta about the financial aspects, basically those checks that had to be cashed, please go see her or email her kind of as soon as possible, okay? It's just a few people, maybe 3, 5 people in the room, but we need to talk to her, okay? So if somebody in the room has not cashed their checks, you need to go see Nicoletta. Don't go on your own to Trieste or something, okay? So maybe just to let you know what the idea of today's lectures is going to basically to continue a bit on electron-phonon physics first, then specialize on theory of transport, and that will be Samuel Ponce, and then we will go to discuss EPW, first the code and then the hands-on in the afternoon. So if we are all here, I think I would like to get started because we have quite a few slides to go through, so it's better to... Okay, basically what we want to do now is to continue the discussion on electron-phonon physics, okay, at a very fundamental level. And so if you remember yesterday morning, we discussed a very simple way of talking about electron-phonon problems, and that's elementary perturbation theory, okay? And the idea is that using those techniques, which are standard textbook rules, we can understand some of the key concepts. So in this lecture, what I would like to do is to raise a few warning flags in the sense that not everything can be done using elementary perturbation theory. And if you want to be more predictive, or if we want to solve some specific issues, we need to develop some more advanced theories. And that essentially goes in the direction of many-body techniques. So what we are going to do this morning and tomorrow morning is to introduce a bit the language of field quantization and see how that can be applied to electron-phonon problems. So I need to tell you in advance that this is going to be more complicated than yesterday. We're going to have a few maths to go through. And when I was preparing the lectures, I was wondering whether one should give any maths or not. But the point is that this is supposed to be an advanced school, and all the lectures will be available, are already available online. So I prefer to tell you the whole story, maybe not with all the steps, so that, if you're interested, you can go back home and look at the slides or look at the literature, as opposed to simplify too much the picture, okay? So let's see what we're going to discuss. So first of all, I would like to tell you why we need many-body techniques, basically bringing a few examples of where the perturbation theory yesterday failed miserably. And then we're going to introduce essentially the language of many-body quantum field theory and then Green's functions. And we will end up basically discussing what we call the electron-phonon self-energy, which is essentially the quantity that we calculate when we want to do calculations of electron-phonon interactions. So for example, yesterday you've seen this quantity lambda. That's essentially something that comes out of this electron-phonon self-energy after making a lot of approximations, okay? So we will see how to get there today and tomorrow. So let me get started by reminding ourselves what we said yesterday. So we started from basically the Kohn-Sham equations, because we do DFT calculations after all. And we say that we can basically understand electron-phonon interactions by observing that the equations give solutions which are parametric in the nuclear coordinates, okay? That's a very simple statement. There is nothing really complicated. So one thing that we can note from this equation is the following. We have basically electron wave functions. These are the Kohn-Sham states. But we don't have nuclear wave functions. All right, that's number one. And the second is that there seems to be some atomic positions here, and this seems to describe classical particles. So if you can specify just the position of a particle, it means that it's kind of a classical object. So these two things come from two approximations. One is called the adiabatic Born-Oppenheimer approximation. This has been mentioned by Paolo Giannozzi on the first day, actually. Mathematically speaking, that corresponds to saying that if you start from a wave function describing electrons and nuclei, you decided that too much, and you want to simplify. So you replace it by a product of two wave functions, one for the electrons and one for the nuclei, okay? And this decoupling is motivated physically by the fact that typically nuclei are much heavier and then slower, and therefore the dynamics are decoupled. So there is this thing which is pretty much intrinsic to every DFT calculation, okay? It's there from the start. And the second approximation is that not only we decouple the two wave functions, but we also say that the nuclear wave functions are so narrow, because the nuclei are heavy, so they don't move too much. The wave functions are so narrow that we can replace them by Dirac delta functions. So we forget the fact that nuclei are the quantum particles, and we replace them by just classical positions, velocities, and so on. So that's basically the two key things that exist in DFT, and that's a bit of a problem in the sense that if you want to do electron-phone interactions, that's sometimes not enough, as you will see in a second. Then there is another problem which is specific to real implementations of density functional theory. So the self-consistent potential in an ideal world is an exact quantity, but in every calculation that we perform, we need to make a choice of an approximate exchange and correlation functional. So really, since everything depends on this exchange and correlation functional, also the electron-phone interactions will be dependent on the on this functional. So the question is, if you do a calculation of electron-phonon properties using, I don't know, LDA or PBE or the scan functional, is that okay? Or should you use the hybrids, or which hybrid? Okay, that's basically the usual problem. And what turns out is that if you use different functionals, the numbers are different, actually. They can be quite different, okay? So, it's difficult to be predictive when you cannot, when things depend on a functional. So really, the last thing that we have not considered yet is that yesterday we said, oh, we can displace things, do perturbation theory, and then use some vibrational eigenmodes and eigenfrequencies. And we were implicitly assuming that you can calculate those phonon eigenmodes and frequencies. So on day one, you calculated phonons, eigenmodes, and eigenfrequencies using density functional perturbation theory, okay? And if you think about the process, those are numbers obtained by taking second derivatives of the DFT total energy with respect to displacements, okay? So you just move the atoms and take energy differences. And that corresponds to static displacements, okay? So that basically is saying that you are assuming that if you move an atom, the electrons will have enough time to relax to their ground state so that you can use DFT, okay? So this is not always the case. There are cases where this doesn't work. So let's see basically a few examples where these things are not enough. So this is actually one of the prettiest measurements on the conduction band bottom of some oxides. So what basically this is energy axis and wave vector. And this object is the conduction band bottom of strontium titanate. It's an oxide. Okay, it's supposed to be an insulator, but the experimentalist managed to dope it a little bit. So you see a little parabolic band, okay? So the issue here is that in addition to this parabolic band, people see another object here, and then another object here, and another object here. And all of these are separated by roughly the same amount. And it turns out that this energy difference corresponds roughly to the longitudinal optical phonon in this material. So it was assigned to some kind of electron-phonon interaction. So if you try to do Rayleigh-Schrödinger perturbation theory, so what we said yesterday on this kind of experiment, you would only get the first band, okay? Just a little bit of a change of the eigenvalues, but you will never be able to get these replicas, okay? So this is an effect which goes beyond a simple Rayleigh-Schrödinger perturbation theory. Let me show another example, which actually is in every textbook. Yesterday we mentioned superconductors. And in superconductors, there are two things. One is that if you go below the critical temperature, the resistivity drops to zero, okay? Another manifestation is that these are metals, and if you go below the critical temperature, there is a little bit of a gap opening at the Fermi surface, okay? So it's no longer a continuous density of states, but there is a gap. And this can be measured by, for example, scan and tunneling spectroscopy. So this is basically a STS measurement, okay, with a tip on top of an iodine disulfide in this case, which is a superconductor with 6 Kelvin superconducting critical temperature. And below the critical temperature, if you scan the density of states around the Fermi level, you see that there is a gap. So essentially there is a depletion of density of states at this point, while in the metallic states, this will be continuous, okay? So this thing cannot be captured by what we discussed yesterday, okay? This is not an effect that you can obtain by simple perturbation theory. And that's on the side of electrons. But in the electron-phonon interaction, there are two sides, electrons and phonons. So one can also look at an example for phonons. So you're all familiar with graphene. That's just a ball and stick model, found on the internet. I found it fancy, so I wanted to put it there. But the point is that, so this is a very nice experiment on the phonon frequencies of graphene, okay? So the Raman G peak is essentially the highest optical mode at gamma in graphene, okay? It's a vibrational mode at about 200 millivolts. So what they did here is basically to do a measurement of the Raman peak, so the frequency of the phonon, in a kind of transistor configuration. So there was a gate on graphene, and they were able to change the gate voltage. That means that you can raise or lower the Fermi level in graphene, okay? So if you do that in the experiment, you find these dots, okay? So essentially, as you increase the gate voltage, so the electron concentration, basically the phonon frequency increases. What you can do to try to reproduce this experiment is to take density function perturbation theory, okay? And you perform several calculations with different Fermi levels in graphene. You just repeat them, okay? By changing the number of electrons in your unit cell. So if you do that, actually, you obtain the dashed red line, okay? So density function perturbation theory gives you this line. So essentially, there is almost no change whatsoever in the phonon frequency as a function of electron concentration. And this is, again, something that goes beyond simple perturbation theory. So one has to do a bit of a better theory to understand this kind of phenomenon, okay? So how do we proceed in this story? Well, there is only one way out. You need to go back to the basics of quantum mechanics and see how to proceed and try to describe things as accurately and generally as possible in order to capture as much physics as possible, and then cut here and there when we cannot proceed, okay? So the most general starting point, maybe I'm going to show on this side to please the other side of the audience. So the most general starting point is the Schrödinger equation for electrons and nuclei. The idea is that we want to describe a many-body wave function for the electrons and the nuclear variables, okay? And this will have a lot of terms, but they're very simple. So this is the kinetic energy of the electrons. This is the kinetic energy of all the nuclei. This is basically, if I call V the Coulomb repulsion, this is basically the attraction between electrons and nuclei. So this is evaluated at the position of each electron and each nucleus. So basically, this is the electrostatic potential, which is basically 1 over the distance between the electrons and the nucleus. That's the same, but is the repulsion between the two nuclei, and that's the repulsion between each pair of electrons. So that's just the many-body Schrödinger equation. You see that in every introduction to density functional theory. There is nothing really difficult. And the important bit of this equation is that there is both electrons and nuclei, and everything is symmetric. So if you look at this, I mean, it's not that the electrons are better or something. I mean, the electrons and the nuclei have the same kind of dignity in this equation. The main problem with this equation is that basically something which is pretty much impossible to use for any practical calculations. So I'm sure that you know that if you that you can solve the many-body Schrödinger equation using quantum Monte Carlo methods, but if you think about it, quantum Monte Carlo methods are done for the electronic part of the wave function. So you don't see quantum Monte Carlo methods for the complete many functions, wave function, including also the nuclei. That would be atrocious. I mean, nobody can do that, okay? So we basically need to develop a formalism where you can really tackle this problem in a way that actually is even at the level of formalism is feasible. So that's what we're going to do in the next few slides. Before going there, I just want to mention two things. That so one thing is that, as I say, the problem is symmetric. Electron-phone interaction is not only about electrons; it's also about phonons. And in the same way, the lattice vibrations have an influence on the electronic properties. Also, the electrons have an impact on the vibrations. For example, this plot I showed for graphene. In that case, you change the filling of the band structures, and you have an effect on the phonons. Okay, that's something we would like to describe. So in these following slides, I will concentrate on the first half of this plot. So it's basically how the phonons affect the electrons. And then tomorrow, what we're going to do is the reverse, so how the electrons affect the phonons, okay? So these are quite different avenues, but the starting point is common to both. So the first thing that I want us to consider in this story is that if you want to work out with the many-body wave function, the situation is not as simple because you have a lot of variables, okay? So doing maths on a lot of variables is a bit of a tragedy. If you want to derive useful equations, it's very difficult. So people invented something that I'm sure many of you know, but I want to recap, which is essentially called field quantization, which is just a very powerful mathematical tool to handle systems with a lot of particles, okay? So to explain it in very simple terms, I want to use an example. Suppose we have a wave functions of electrons, so in many variables. So we have, I don't know, 20 electrons here. And the most general way to describe this wave function, for example, could be the following. I do a DFT calculation, okay? Suppose silicon, do a DFT calculation. I get Kohn-Sham orbitals, all right? And then from that, I build a slated determinant, okay? So you remember what is a slated determinant, right? It's a symmetrized product of all these occupied wave functions. So that's basically what I call my, let's say, DFT ground state, 0 Kohn-Sham, okay? So that's just a possible function. And that's not the most general function I can look at. So there is actually a machinery in this, in quantum field theory which acts in the following way. So people define an operator which is called a distraction operator that you've seen many times. And that object is simply a mathematical operation which does the following. If this is a kind of determinant, so that operator creates a new determinant where the state, let's say, the Kohn-Sham state n has been removed, okay? So it's a determinant with one less electron. And then what one can do is to, for example, take this, which is a determinant with one less electron, and act on it with another guy, which creates an electron. So this generates a new determinant now with plus one electron. So if you operate with both of them, you end up with a determinant which has the same number of electrons as the original one. Now, the trick here is that this new determinant is not the same as the original one, so you just modified a little bit this wave function. And if you do a lot of these modifications, you can generate essentially all the possible determinants which differ from the original one by essentially removing an electron in a certain state and placing it in another state, okay? So this object in quantum chemistry is called essentially single excitations, okay? And you can do the same operation by doing this maybe by removing two electrons and adding 2 electrons somewhere else. These are called doubles, and then you can go to triples and things like that. So this is something very standard in quantum chemistry. So the only reason why I'm putting here is that the idea is that instead of focusing on a wave function with these space variables, it is basically convenient to start focusing directly on these operators. So that makes life much easier, as we're going to see in a second. So the basic theorem of second quantization basically is that if you have an operator in first quantized form, so basically suppose you have the kinetic energy of the electrons. So in a many-body form is that the sum of the kinetic energy of each electron, okay? And that depends on all the variables that you're looking at. So electron 1, electron 2, and so on, okay? So you can prove, and that's done in pretty much every textbook on advanced quantum mechanics, that is exactly equivalent to writing this operator in this form, where these are the matrix element of the operator in the single particle representation, for example, Kohn-Sham orbitals, and then there are these two creation and destruction operators. So that's just a mathematical kind of statement. We're not gonna prove it because actually it's quite tricky to prove, but you can find it, even on Wikipedia if you like. The point is that if I now write down this in an explicit form, you will see that things get actually quite easier. So this object is basically this thing here. I say this is the matrix element of this operator, can be a potential or a kinetic energy, between, let's say, Kohn-Sham single particle states, okay? So I can just expand it like that. And now if I color the bits with the same index, what you see that I have a sum over, let's say, n, wave function, let's say Kohn-Sham wave function n, and then this distraction operator with n. So if I put it together, actually, I can define a new operator, okay, which actually looks pretty. It's essentially a linear combination of these discrete distraction operators, and the coefficients are the value of the Kohn-Sham wave function at a given point. So this is basically numbers, operators. So this is an operator, okay? And this operator depends parametrically on this variable. So essentially, I'm defining a new operator which now does not depend on discrete coordinates, but on a continuous coordinate, okay? So this object has a name, it's called a field operator, okay? That's just a definition so far. One sec. So if I place this back on the expression, basically what you see is that I can basically rewrite this red bit as a field operator here, and then what is left has a similar shape, and therefore I have psi dagger v psi. That looks very much like the matrix element in single particle quantum mechanics, but these are not wave functions. These are actually operators, okay? So formally, it's identical. Practically, it is not, but it is useful to have a very simple expression like this as opposed to work with a lot of variables. So you had a question there? Yeah, that basically goes wherever you like, basically. It's yeah, that's correct. I mean, basically, I just mentioned the FT to give an idea of what one could do. In principle, I mean, this formalism does not depend on the, so this is just a choice, okay, of, so these functions here are a choice of a single particle basis, okay? In fact, in textbooks, if you go to, textbooks describing second quantization, they start from a basis set of plane waves in the, in the 50s, studying the electron gas, okay? But because that's what they were used to work with. I mean, I could have said, oh, let's start from plane waves. It's just that it's easier to think in terms of DFT orbitals because we always calculate those, essentially. But let's say the formalism does not depend on the underlying basis, okay? Because in the end, really, we have an operator, and when we describe it using a field operator like that, this will become basis set independent in practice. Okay, so that's not an important. So essentially, the DFT assumption is only to define this thing, but it's not been used in practical calculations so far. Right. So the x here is basically, you can see it as the position, if you like, or if you want to think about, let's say, so if you want to make the connection with local spin density approximation, you can think about position and spin. It's not really important in this context, but let's say it's the position of the particle. Okay. So, given this formalism, the point is that we can rewrite the entire many-body Hamiltonian, so the one that I gave you earlier with a lot of terms, just in terms of these operators. And if we look at a couple of, so this basically is the kinetic energy of electrons, nuclei, and then the electrostatic terms. That's what I gave you earlier. This can be rewritten in a much simpler way. For example, the kinetic energy of the electrons is simply, instead of adding up the kinetic energy of every particle, we just write it as the kinetic energy operator sandwiched between these field operators now. So there is only one bit. Now, clearly, the physics is the same, and the operators are more difficult to work with than just wave functions. But you can see that instead of writing, I don't know, if you have 100 electrons, you would have 100 terms. There is only one in this case, okay? So for the electrostatic repulsion, attraction, between electrons and nuclei, in this formalism, this takes a very simple form. So this is the Coulomb potential, 1 divided r minus r prime, okay? And then what we do is to just calculate the Hartree energy. That's electron density, and this is nuclear density. So it's basically the electrostatic energy between two distribution of charges. So that's as simple as that. The difference is that these objects are not the densities of electrons and nuclei. These are actually the density operators, okay? These objects are not just simple functions. And the good news is that the density in second quantization is, takes a form which is very nice. It's basically simply psi dagger psi. So if you think about the density in, in Concham, that's basically sum of the occupied psi square, so psi star psi, okay? So in second quantization, it takes a very similar form, but again, these two objects are operators. They are not wave functions. So that's basically the trick to proceed. And finally, for the electron-electron interaction, we need to use a similar term. So that's again electrostatic energy. So it's the electrostatic interaction between electrons at one point and another. So it's basically electron density at a point r times electron density at points r prime divided their distance. Okay. And the only difference here between the first expression and the second is that for the electrons, we need to take out the self-interaction. So if you calculate this quantity at the same point, this would explode. because you have one divided r minus r. So to avoid that, basically we need to take out the contribution where two electrons find each other at the same point. So if you try to expand these expressions, essentially, using this definition of the density, you will find basically a Hamiltonian, which depends on a lot of field operators, okay? That's the standard expression you find in textbooks. Now, let's see a little bit what we can do with these things. So in the next few slides, I will give you 2 or 3 definitions that we need. And where we are going to is to try and see how we can study the electron dynamics and how to get to some formulas, and then we can implement in a code and get some physics out, okay? So first definition is that if I take this Hamiltonian and I apply it on the ground state of the system, I get an energy, okay? So that's an eigenstate of the many-body system. I get capital E sub n, and that's my ground state energy for a system with n electrons, okay? That's just the definition. Then let's imagine a situation where you add an electron to the system, okay? And you add this electron in an excited state. So what you can say is that the Hamiltonian acting on this new excited state, so n plus 1 particles, excitation number s, will give you an eigenvalue, E sub n plus 1, for this specific excited state. So this is many body states. And to understand this, let's think of a semiconductor, for example, okay? The conduction band is unoccupied. You inject an electron, let's say 2 electron volts above the conduction band bottom, okay? So that would be an excited state of the system, which is not the ground state. But there is 1 extra electron in the system, okay? So that's the physical picture here. So if you take the difference between these 2 energies, that defines the excitation energy, and that's precisely what actually is measured in experiments. So this energy is what the price you pay to extract an electron, or the energy you gain to place an electron in the system, okay? So that's exactly what is measured for the emission spectroscopy, and this is the kind of quantity that is relevant when you have, for example, a transistor and an electron is moving from one side to the other, okay, through the channel, from the source to the channel and things like that. So this is the concept of addition and removal energies that you find in GW calculations, for example, okay? So in a more simplified picture, this would be, for example, the Kohn-Sham eigenvalue, if you want, okay? So the Kohn-Sham eigenvalue is the friend of that, but after a lot of approximations. Now, in order to work with this formalism, we need to introduce something which is the time evolution of the field operators. This is basically done in the Heisenberg representation. So if you remember your quantum mechanics, you can either evolve the quantum states or you can evolve the operators. So in this case, it's convenient to evolve the operators. And the way it works is that you basically perform unitary rotations of the field operator, and you use here the Hamiltonian, which generates the time evolution. So that's basically something standard in quantum mechanics. And the useful thing is that if you take derivatives of that, you obtain the Heisenberg equation of motion, okay? So that's really nothing advanced. This is something that you find in any textbook on quantum mechanics. The reason why I'm showing you this is that we can try to do a little exercise to see what happens if I try to squeeze this operator inside, so in between 2 many-body states, all right? So let's, for example, take the ground state on the left, okay? And then the time-dependent field operator here. So this is the distraction operator acting on the right. And then this is the excited state. So if I use the definition, this is basically the, I replace this time evolution here inside this, in the center of the bracket here. And what you can see is that the Hamiltonian here can act on this state. Since this is an eigenvalue, an eigenstate, I pull out an eigenvalue, and therefore this will essentially give me an eigenvalue in the exponential. And for this, by the same token, this Hamiltonian acting on the left, since this is the ground state, will give me this eigenvalue here, essentially. So I will find these 2 eigenvalues in the exponential, and therefore I can put them together. What is going to happen is that since their difference is the excitation energy, I have simply an exponential here, a complex exponential which evolves with a frequency corresponding to the excitation energy divided h bar, okay? Now, the interesting trick in this story is that if you look at what is left, that's the many-body state with n electrons. This field distraction operator acting on an n plus 1 electron system, and this bracket is really an integral over all the electronic coordinates. So if you have 10 electrons, there will be an integral over 10 variables, okay? And everything checks out because this has, let's say, if n is 10, this would be 11 electrons, okay? But this guy destroys 1 electronic state. This would be then a function of 10 variables. And this guy has, again, 10 variables. So you have an integral over the right number of variables. And this will be a number because, you know, it's just an integral. It's going to be a complex number. And the interesting bit is that when you evaluate that, this number will be parametrically dependent on this coordinate, okay? So in a sense, you can say that this number is this bracket will lead to a function which depends on position. So this function has a name. The name is Dyson orbital, okay? So that's, in a way, is the friend of the Kohn-Sham orbital, but in many body theories, all right? So that's basically the closest friend to the Kohn-Sham orbitals. If you want, let's say the Kohn-Sham orbital is the poor relative of this one. So this is you know, the big guy, the good guy, and the Kohn-Sham orbital is after doing a lot of approximations and seeing what is left, okay? But it's really the starting point. So this is to say that if you look at this strange matrix element, you get a Dyson orbital times this complex exponential. And now this allows us to look at the Green's function, which is really the star of the story. So the Green's function is an object which is defined as you see there, and I will try to explain why we do that and why this is useful. So this is basically a function which is found everywhere in many body theory. It's basically a function of two space-time variables. So space coordinate and time coordinate, space coordinate, time coordinate. So it's describing essentially two space-time points in our kind of system. And basically this coordinate we refer to electrons. And we're going to see in a second that that corresponds to the propagation of an electron. So the definition is this one. It's a bit of a monster, so that's ground state. This is called time ordering operator. I'll tell you in a second what it is. Field operator, and ground state. So this is a bit difficult to understand like that, but if I color bits one by one. So this blue bit here, if you think about it, that's basically a mathematical object which acts on the ground state and creates an extra electron at this time, at this point, and at this time, okay? So this blue bit is really a new quantum state, which is ground state plus an extra electron at this point and at this time. So if I look at the red bit, which is, it doesn't want to count. Okay, sorry. So the red bit basically is, if you look at it, is the Hermitian conjugate of what I have on the right. So there is no dagger here, acting on this guy. So this has the same meaning, but it's just taking the complex conjugate. So this is again an electron added to the ground state at the point x and time t. So this object is representing the scalar product between two quantum states, one with an electron here and one with an electron there, okay? So when you have a scalar product in quantum mechanics, what you're looking at really is how much of the initial state is contained into the final state. So if you take the square modulus of that, that's the probability that you start from the initial state and you end up in the final state. So for this reason, the Green's function is called the propagator of the electron, okay? So if you know the Green's function, you pretty much know everything about the dynamics of the system. Yeah, so basically this is the piece of information left in this slide. So this is an object which has the following function. So basically its purpose in life is to make sure that the times are ordered in such a way as to increase towards the left, okay? So if the time t, let's say, is greater than t prime, this object does not do anything. If that is not the case, what it does is to swap the two operators and change the sign. That's really a mathematical trick. One can define, so this basically what is called, that leads to what is called the time ordered Green's function. It is useful to work with this for what we want to do today. There are other definitions where you don't have this time ordering operator, and one can define other versions of the Green's function. For what we need, that's essentially the easiest way to define the Green's function, basically. We're going to see why in a second. So let's make an example of what a Green's function can do for us. So if I consider times t greater than t prime, I say that in this case, the time ordering operator does not do anything, okay? So we can just remove it. And what I can do at this point is to replace in these field operators the expressions I gave you earlier with the Heisenberg time evolution, okay? So instead of that, I will place this bit here. So the Hamiltonian generating the evolution of this object. And instead of this guy here, I can place this bit. So here, what you can see is that basically the Hamiltonian on this side acts on the ground state, and will pull out an eigenvalue on the exponential. The Hamiltonian on this side acts on the ground state, and again pulls out an eigenvalue. And then these two, they commute because it's just a number times the Hamiltonian. So if you put them together, hopefully, basically you have this eigenvalues coming from this and from this coming into here, and the t minus t prime coming from that grouping together here. Okay, so that's basically just a development of this Green's function. So now this is still not very pretty, but we can do another trick using the exercise I made in the other slide. So what I can do here is basically to insert, a resolution of identity. Basically, I can expand over all possible states of the system with n+1 electrons. That I can always do because this object is equal 1. Essentially, it's a complete basis set. So if I do this trick here, you can see that the reason I'm doing is that I'm going to end up with a ground state, field destruction operator acting on this object. So that's precisely this thing leading to the Dyson orbital I gave you earlier. And then this Hamiltonian acting on this object will pull out the eigenvalue of the excited state with n+1 electrons. So this basically will give me a Dyson orbital. And if I place the same resolution of identity on this side, I get again a Dyson orbital. So if you look at the math, it takes a bit of time to go through that, you find that basically the Green's function is just the product of these Dyson orbitals, one, so at x and x prime. This is normal, this is a conjugate, and then I have this time evolution in the exponential. Okay, so that's basically what a Green's function would look like in real space. And if at this point you're getting lost, the easy thing to do is to just think that this could be the functions that you calculate in DFT. So this could be Kohn-Sham orbitals, and this could be Kohn-Sham eigenvalues, okay, if you want. So that would be a brutal approximation, but that's something that one can think of. So really, the Green's function has this kind of shape if you want to work in the space domain. Now, if you look at this object, okay, there is it depends on the time difference, and people don't like to work in time domain. If you do calculations, we like to work in the frequency domain, or if you want energy domain, because in the end we want eigenvalues. So what one can do is to do a Fourier transform of that and obtain the Green's function as a function of x and x prime and a frequency omega, okay, instead of the time difference t minus t prime. If you do this trick, basically this exponential leads to 1 divided this omega minus the excitation energy, and that's the standard form of the Green's function that we see everywhere and that we use practically in calculations, okay? So if you look at this object, it is telling us that the Green's function is the product of two orbitals, okay? In the general case, it has Dyson orbitals. If you are doing DFT, this would be Kohn-Sham orbitals. And in denominators, you have the frequency minus the excitation energies. So the most important result of this story is that if you can calculate the Green's function, the poles of the Green's function, so this object, give you the excitation energies of the system, okay? So if you work with, instead of a many-body Hamiltonian, you work with a DFT Hamiltonian, the excitation energies will be just the Kohn-Sham eigenvalues. But if you want to go beyond that and use the full many-body Hamiltonian, what you get out of this will be the many-body excitation energies, okay? So that's why we are doing these things. So the trick at this point, after realizing that to get the excitation energies, we need to look at the Green's function, is to try to understand how to calculate the Green's functions, okay? And when I talk about excitation energies, really what we need to keep in mind is that's basically the band structure of the system. That's what we're talking about. So there's nothing really sophisticated. But it would be a band structure that includes all the interactions that I squeeze in the Green's function, okay? So the game now is to try to see how to have as accurate as possible Green's function to incorporate the interactions we want to look at. Now, from the Green's function, people like to define another object, which is called the spectral density function, which is something which has a strange name, but if you think about it, it's something you've been working on every day, essentially. So if you look at this and you take the imaginary part, what you realize is that essentially is a delta function, okay? So if you take the imaginary part of the Green's function, you obtain and you evaluate at the same position, that's basically something where this function appears with the square modulus, and then you have delta functions. So this object should remind you of something. That's basically the definition of the local density states in DFT, basically, okay? The difference is that these may not be DFT energies and again functions. So really the spectral function is the many-body generalization of the local density states that we use in DFT. And that is what people use to essentially define band structures in many-body physics. And the other thing, the only last message I want to give you is that instead of looking at in the position space, people like to write down the spectral function by also Fourier transforming the position here into a wave vector. So really one has a spectral function which depends on the wave vector and the frequency. And with that, basically, what we are talking about is a, let's say, a better version of a band structure, really. So that's what we want to do. Let me give you an example, basically. If you, let's imagine, that's just a impossible example, but to make things simple, let's consider it. Imagine that we have calculate a Green's function, and we end up with a single pole, and this pole is not on the real axis, but is slightly off the real axis, just to see what happens. So if I say that my excitation energy is this object with a real number and this an imaginary number here, I replace in the definition of the Green function, the Green's function, what I obtain basically, if I look at the same position, is the square modulus of the Dyson orbital. Then in the exponential, the real part gives me a complex exponential, but the imaginary part, basically the I, basically multiplies this other I here, and therefore I have a real number. So if I take the square modulus, the modulus of that, I basically have a function which decays as the difference in time, as basically the time difference between t and t prime increases. So bottom line is that if you work out a Green's function, you calculate it and you get a complex pole, what this is telling you is that you're looking at a situation where you inject an electron somewhere, let's say in the conduction band, but that probably is not going to be the ground state because the electron does not want to be there. It will decay away of that state. So physically, imagine again you inject an electron, 2 electron volts about the conduction band of a semiconductor. That's not going to be an against of the system. I mean, in a realistic situation with many body interactions, so the electron will decay towards the conduction band bottom. Okay. So this basically the imaginary part of this pole will give you information about the time it takes to decay. So when people want to study, for example, relaxation rates in semiconductors, carrier lifetimes, and things like that, this is the kind of physics that we are discussing. And just to make the connection with the spectral function, if you do the same operation, but for this companion function, the spectral function, it takes a very simple form, and essentially this is a Lorentzian. So the bottom line is that this complex pole will give a Lorentzian with a width of, let's say, gamma in this example, to the spectral function. So if you can calculate or measure a spectral function from the width of the peaks, you can tell the lifetimes of the particles, okay? So basically, if you're looking at an electron gas, for example, that's energy, wave vector, suppose it's a parabolic dispersion. If it happens that the peaks are a bit broad, this means that the particles do not have a infinite lifetime. They will decay at some point. So the broader the peaks, the shorter the lifetime of the particle. So let me tell you now that in the most general case, we don't have a simple pole. So what happens is that the spectral function gets modified from the DFT case quite a lot. So in the case of Kohn-Sham density functional theory, if you try to calculate this thing, you get a sharp peak for each eigenvalue, okay? Because each Kohn-Sham state is an eigenstate of the Kohn-Sham Hamiltonian, so it's a stationary state, so it's infinitely lived. And if you switch on interactions, for example, electron-Phonon interactions, that is going to be messed up a little bit. But typically, you recognize a main peak, so the friend of this one. That's called the quasi-particle peak. This will have been shifted, and that difference from the Kohn-Sham eigenvalue is going to be called the quasi-particle shift. There will be a bit of width, so a broadening, and that essentially will tell us something about the lifetime of this excitation. But then typically there's also some stuff here which you cannot find in using some simple perturbation theory, which maybe has to do with the excitation of some other things in the system. Let me maybe make an example. If you inject an electron in a semiconductor again, it's not going to happen if the system stays kind of immobile, doesn't do anything. So there is a charged particle entering. So for example, other electrons will readjust, and also the nuclei will readjust, okay? So there is going to be a lot of energy dissipated, and that is going to show up in extra structure in the self-energy. So if you want to do something very accurate, you will see a lot of structure that you don't see in density functional theory clearly. Now, let me, maybe I should speed up a bit because the time is running out. So what I want to tell you is that from the field operators, you basically, from this equation of motion, using the Hamiltonian that I gave you earlier, you can derive the equation of motion for the entire field operator. And the beauty of this is that it has a very simple shape in second quantization. So if you think about it, this is the time derivative of the field operator is equal to the kinetic energy operator plus Coulomb potential times the total density of the system. So density of the electrons and the nuclei. So this really, if you remove the hats here, here, and here, it basically looks like the time-dependent Schrödinger equation in the Hartree approximation, okay? So there is really nothing really complicated. The problem is that these are not just wave functions, these are operators, so that creates a lot of complexity. But at least formally, we don't need to deal with a lot of variables. From these guys, what you can do now is to simplify the notation. And I'm showing you this here because if you go into the textbooks, you will see that a lot of people use a strange notation where they replace the variables by numbers. So for example, x and t, so that's position, if you want position and spin, and time. People don't like to write all these symbols. They say, okay, this is 1, okay, a new coordinate. And then if you have, I don't know, integral in dr prime, vr prime, nr prime, it's going to be integral in d2, v12, and 2. So that's a bit crazy if you look at it for the first time, but actually it's quite useful because when you have a lot of integrations and things, it gets very messy. So the fewer variables you deal with, the smaller the probability of making mistakes. Now from that, and we are going towards the final equations, from that basically what we can do is to generate the time evolution of the Green's function. So the Green's function is a product of two field operators, okay? So if we know how one evolves, we can generate an entire equation for the Green's function, and it looks like this. So this is very ugly, as you can see, and that's why these things are not that easy, but we recognize a time evolution, kinetic energy, and then a monster here, okay? And that monster is basically the source of all evils in second quantization. So that monster basically contains a density, a field operator, and a field operator. The density is psi dagger psi, so there are 4 field operators there. And this object basically, if you think about it, it can be seen that, let's maybe imagine that the Green's function has 2 field operators, okay? So when I find 4 field operators, maybe what I can imagine is that this is going to describe not 1 electron propagating, but 2 electrons propagating, okay? So I destroy 2 electrons and I create them somewhere else. So that's going to be 4 objects, and that's what is called a 2-particle Green's function. So in fact, if you do the maths, this object will contain some Hartree term, some Fock term, plus a Green's function for 2 particles. That's basically for the correct motion of 2 electrons. So that's a bit of a mess, okay? And at this point, things get almost hopeless because essentially you do all this kind of sweating, and then you get to an equation for the Green's function, which is what you want. And then you discover that if you do this equation, there is a 2-particle Green's function popping up. And then one can now hope that, you do, okay, let's do an equation for the 2-particle Green's function. And after doing all the maths, there is a 3-particle Green's function popping up. And so you get desperate at that point. So what people did at this stage is to approach the problem from 2 avenues. One is to basically try to address this thing using expansions over Fan-Migdal diagrams. And that's one thing that was done a lot in the 50s. And then there is a second approach, which is what basically has been followed and led to GW calculations, which is basically trying to replace this object by a function called the self-energy, okay? And the procedure to go from this point to the self-energy is called the functional derivative technique of Schrödinger. And I cannot describe it here because it's too complicated. But if you want, in the references at the end of the slides, you will see some reference to that. Point is that this complicated thing can be rewritten in a slightly simpler way in an object by replacing the 4 field operator term with a self-energy times the Green's function. And this starts to look like what you probably have seen if you've done any GW calculations, okay? Now, if I replace the Green's function by the definition using the Dyson orbitals, things become much easier to understand. So we basically get an equation which looks like the Kohn-Sham equations, the difference being that these are not Kohn-Sham orbitals, and this is not the exchange and correlation potential in the FT. It's a much more complicated object, okay? But at the end of the day, if you do everything essentially very, very accurately, you make no approximation whatsoever, you still get to an equation which looks like the standard Kohn-Sham equation, except that the quantities appearing in this equation are much more complicated, and in principle, this contains all the many-body physics we want to squeeze in it, okay? So for example, one of the things that we can tell now is that the electron-phonon interaction enters in this object, as we'll see in a second, and in this object. And the complexity of this equation has to do with the fact that, we have an eigenvalue on the right, but this eigenvalue also appears on the left in the self-energy, okay? So as you can imagine, this is not just a eigenvalue problem. There is another complication, that's the fact that the self-energy is not Hermitian. So basically, the problem to get at the end of the day is not Hermitian. So you're not expecting to get real eigenvalues like in DFT. Sometimes the eigenvalues are not discrete, so you have a continuous spectrum of eigenvalues. So the situation gets quite much messier. So what people do, for example, in GW, is to replace this function by something a bit easier, which will lead to some real eigenvalues, okay? And that's basically the GW quasi-particle corrections. But in principle, that can be any object you want. So the shape of the self-energy is similar to GW, so it's basically sigma equal G, gamma, and W. G is the Green's function. Gamma is called the vertex, I'm gonna show you in a second, and this is called the screen-Coulomb interaction, okay? So that comes out of the equations, and now we cannot do it here, but if you want in the references, this is actually derived one by one. But the point is that this is very similar to the GW method that you might have seen. The difference here is that in the GW method, this is basically the interaction between each pair of electrons screened by the electronic dielectric function, okay? If you want to squeeze in electron-phonon interaction, what happens is that on top of the screening coming from the electrons, you have also the screening coming from the nuclei. So imagine in the GW method, basically, we have the screen-Coulomb interaction, which corresponds to essentially asking what is the Coulomb interaction between two electrons injected at 2 points, okay? And that has to do with a lot of rearrangement of the electronic charge. And in that method, we completely ignore the fact that nuclei may also rearrange, okay? So here, what happens is that on top of that contribution, there is another contribution coming from the rearrangement of the nuclei. So if you add 2 electrons at 2 points in a solid, okay, not only the other electrons will rearrange, but also the nuclei. And that will lead to some extra screening, which essentially contributes to self-energy. So the electron-phonon interaction, in a way, comes from this extra contribution to the screening. Now, let me tell you the shape of this screen-Coulomb interaction for the phonons. So that's a bit messy, and I don't want you to remember it, but the bottom line is that it contains 2 objects, which are the friends of the electron-phonon matrix element that we calculated yesterday, okay? So that's basically the main mathematical structure. And in the center, there is an object which is called the phonon-Green's function, and that's essentially the equivalent of the electron-Green's function, but for the nuclei. The definition is that I take the ground state, I act on it with an operator which creates a displacement of a certain atom at a time t, and then I look at the overlap with another state where there is the ground state plus a displacement over another atom at another time, okay? That's basically the propagation of ionic displacements, and it's called the displacement correlation function. So I know that this all, it seems very awkward, but that's the way to go to do electron-phonon interactions. Now, if we consider this is W, matrix element, propagator. We can probably represent it more easily, visually, in this way. So this is what people call the propagator, is a wiggly line. So this would be the 2 matrix element I told you. And if you remember the expression sigma equal G, gamma, and W, basically we have G, the Green function, gamma, the vertex, and W would be this 2 matrix element and then the phonon propagator. So this is basically representing these mathematical expressions I gave you before. And as you can see, things are actually quite messy. I mean, it's quite complicated. So sometimes in textbooks, you see that people just write down, oh, this is the Fan-Migdal diagram, and that's easy. Well, it's not easy at all, actually. There is, a lot of variables involved, and there is a lot of maths. So this is actually the end point of a lot of maths. So you cannot just write this, okay, this is Fan-Migdal diagram, and that's it. It doesn't work, okay? You just cannot make any predictive calculations. So this is basically for the electron-phonon. This is the standard GW diagram that you might have seen. It will be Green's function of the electrons, screen-Coulomb interactions, and the vertex. So that's basically what is calculated in things like Berkeley GW, VASP, Yambo, Abinit. Okay, that's basically the kind of diagram that is calculated. But this is the one that we need for the electron-phonon interactions. So in the following, I'm going to give you examples of this guy, and ignore that because this is really about GW calculations, not about electron-phonon physics. I just want to say that there is another guy here that I did not mention so far, and it's called basically so this was called the Fan-Migdal self-energy. This is called the D by Waller self-energy. It's a new object, and one can say, where does the hell this come from? If, I just described a lot of things, but I never mentioned something like this. Well, the reason for this is that this is not really a self-energy. This guy, actually, if you allow me to go back a few slides. So this is unforgivable, but I need to do it. Okay, if you remember here, I say that the electron-Phonon interaction comes from this self-energy, okay? That's what the diagram I showed you. But there is another bit coming from this total potential, okay? The bit of the total potential is quite interesting. Comes from the fact that this, in principle, would be the electrostatic potential generated by the nuclei. So that would be the ionic potential in DFT, okay? But in a many-body framework, the ions, so here, they are not point charges, okay? They are quantum mechanical objects. So their wave functions are not just a sharp delta function, but they're something a bit fuzzy, okay? So this fuzziness changes a little bit the distribution of the nuclei, and this change is felt by this total potential, okay? So the potential is not sharp, it's something which is a little bit more fuzzy. The term that describes this kind of effect is this d by water self-energy that I indicated in this diagram, okay? And the fact that this Green function folds on itself is simply a way to say that this is not really a Green function, this is a density. So if you take the Green function at the same space-time point, that's basically the density of the nuclei. And that's why it does this kind of strange fold. But that's just a way to call everything self-energy, although this is not really a self-energy. Now, just an example to show you what happens if you incorporate these things. What we do in practical calculations is to neglect the vertex, because it's difficult, and to replace the Green's function and the phonon propagator by DFT calculations. So we replace the Dyson orbitals by Kohn-Sham orbitals. We replace the phonon propagator by calculations based on density function perturbation theory, and we proceed from there. Let me show you what happens if we write down the expressions. So this is basically the self-energy that we obtain if we make these approximations. And that's actually the expression that is implemented in EPW, okay? So that's basically something which involves square modulus of the electron-phonon matrix element, okay? So this would be these two guys. And then these terms here come from the product of the Green's function of the electrons and that of the phonon. And that is seen in the fact that you have some electron energies and some phonon energies, okay? That's why they are both in the denominators. So this object, basically now, is telling us that if you are looking at the electron-phonon self-energy here, it will be an object with a lot of structure on very small energy scales, okay? So if you look at the poles of this object, there will be poles near phonon energy scales. So that's something that needs to, probably will lead to some interesting effects. There is also an integration over the Brillouin zone. So that is why we were saying yesterday that you need to sample your Brillouin zone very efficiently, because all these self-energies require you to use a lot of K points and Q points to get the integral correctly, okay? So it is not enough to just sample, 888 points, something like that. You will see now in the following lecture that we need sometimes, millions of K points to get these numbers right. And the last thing about this equation is that I told you everything that about zero temperature. So the formalism I described is about zero temperature, but we need properties at finite temperature. The formalism is much more difficult, but fortunately the result is not too different. So at zero temperature you get that, where these are occupation factors, so either occupied or unoccupied electronic state. At finite temperature, this becomes the Fermi-Dirac distribution, and then we add the Bose-Einstein population. So actually this requires a lot of math work, but the result is very, very similar to the zero temperature. So we are pretty lucky in there. But the bottom line is that now we can look at self-energies as a function of temperature. So I want to give you an example, and this is basically for the electron gas. That's the simplest possible system you can look at. So that's basically parabolic bands, okay? And I want to focus on a system near an area near the Fermi level, okay? So that's basically just a metallic homogeneous electron gas. And we want to switch on the electron-phonon interactions and see what happens here. So I'm going to consider what is called a Holstein model. That's basically a system with just one phonon and a constant matrix element, okay? So that's really the simplest thing you can think about. And you can calculate the self-energy, it can be done analytically in that case. And you can add the self-energy to the spectral function to see what happens. So if you start from the dispersions, so I'm zooming here. So these are basically the dispersions are almost linear near the Fermi level. If you switch on electron-phonon interaction, something interesting happens, basically. This thing generates peaks which are very sharp here, but then they become very broad. So it's a side view and top view. So you can still follow the bands. So this was the original band, and then you can follow the maximum of this function. And as you can see, basically there is some deformation of the band structure near the Fermi level. Now this deformation happens on an energy scale which corresponds to the phonon energy. So there's only one phonon in this example. And there are two main effects. Basically, the first effect is that the velocity, so the derivative of the band is changing near the Fermi level. And the second effect is that things become very broad, okay? So these are typical electron-phonon effects that you can expect from these self-energies. And this really comes from this self-energy equation that I gave you. I mean, if you squeeze that in the Green's function, you get this result. So is this useful at all? So if you look at the experiments, this is what I described yesterday. So this is basically an RPS experiment on magnesium diboride. So people can measure the spectral functions now, okay? And the dashed line would be the DFT result. And if you look at the experiment, actually there's this kind of wiggle here, which is precisely what I just described, okay? Is this change of the velocity coming from electron-phonon interaction. So that's not unique to magnesium diboride, but in this case, basically, the change of velocity is very significant. So basically here near the Fermi level, the velocity is changing by a factor of over 2, above 2 with respect to the DFT. In the case of, I don't know, graphene, the people measure similar things, but the renormalization is much smaller, so it's just 25% renormalization. So that's why we say in graphene, the electron-phonon coupling is quite weak, okay? But this effect exists in both cases. So you see the kink here, the kink here, this kink here. So this is very typical. And these are some calculations. Maybe I will not spend time on this. This has been done by Roxana Margine, who's going to talk on Friday about superconductivity. And basically, that's again a graphene material, and there are some kinks. And that's on MGB2, which is more dramatic. So in MGB2, basically, well, you cannot see well, but there is basically this kind of kink near the Fermi level, which corresponds to what has been measured experimentally, okay? So some terminology. You can see in these things that there is still some kind of band structure, so we recognize some lines there. So people don't want to completely abandon the concept of band structures, so they like to define what we call quasi-particles. So the idea is very simple. If you have a complete self-energy, which is a mess, but you still can recognize some peaks, people say, let's expand the self-energy near the Kohn-Sham eigenvalues, for example, or near the final eigenvalues. So if they do this expansion, basically, sorry for that. Basically, you take the self-energy, you take the value at the eigenvalue, then plus the derivatives times the difference between the frequency and the eigenvalue, and then you can replace this object inside that expression, okay? And to do that, basically, people introduce some new quantities. One is called the quasi-particle strength, which is basically a friend of this derivative. And the reason to do that, maybe I'm going to accelerate a second, is that if you do this trick, you find a very nice expression for the self-energy, which is simply some poles which have complex energies and which have a strength given by this quasi-particle strength. So if you do a brutal approximation to your system, you end up with essentially a deformed band structure. The peaks in the band structure no longer have a weight 1, they have a weight of z, okay? If this z is very close to 1, we say that the quasi-particle picture is adequate. If the z goes close to 0, then probably you are in the regime of dense dynamical mean field theory and things like that, okay? So quasi-particle picture, not good. In most of the things we do, z is between, say, 0.7 and 1, let's say. So things are okay. This new eigenvalue is obtained, let's say, from the Kohn-Sham eigenvalue by using the real part of the self-energy. And the broadening is obtained from the self-energy by taking the imaginary part. So bottom line is that basically we can calculate the self-energy. So this is what we calculate in EPW. The real part gives us the shift of the energies that we calculate in DFT. The imaginary part gives us the broadening. So the inverse of that is the lifetime. And the derivative at the Fermi, so let's say at the eigenvalue is related to the strength of the quasi-particle, okay? So how much area is under the peak that we are looking at. So finally, I just want to mention that these things are useful to calculate, for example, changes in the effective masses in semiconductors, because you can take the quasi-particle energy and take derivatives with respect to wave vector. So the change in the effective mass is 1 plus lambda, and this lambda is the friend of the lambda that we discussed yesterday. The difference is that this does not apply to the entire Fermi surface of a metal. This is for any state in any kind of system. And the definition of lambda is actually mathematically is very simply the derivative of the self-energy at the eigenvalue that you are looking at, okay? So this is also another quantity that we can calculate using EPW. So this is basically useful if you're doing, for example, studies of transport, and you want to, somebody tells you, oh, you know, in your system there are polarons, so what do you do about that? Well, polaron just means that the mass of the electron is going to be a bit heavier, so what you need to do is to calculate this mass enhancement and squeeze it into your effective masses, basically. That's pretty much it. Finally, I just want to say that you can also get the electron lifetimes, and if you do some brutal approximation, okay, you get an expression which has a simple physical meaning. Basically, the lifetimes involve the matrix element square and some terms which are actually corresponding to the emission of a phonon or the absorption of a phonon, and that's the same thing that you would write down if you were to do the Fermi-Golden rule expression, okay? But this is a simplification. This is not the full result. So for to get the complete relaxation time, you need to incorporate the quasi-particle normalization. You need to evaluate the energy of the quasi-particle energy. So things are a bit more subtle than they look, but at least physically, it is reassuring to see that after all the many-body kind of complicated derivations, we end up with expressions which are very kind of sensible from a physics standpoint. So these are just some example calculations of the lifetimes. This has been done by Carla Verdi, one of the TAs here. And this is the conduction band bottom of titania. One can calculate these lifetimes, and you can see that actually they are very large near the band bottom because you cannot scatter into anything. But as you move up into the conduction bands, there are many more scattering possibilities for scattering, and the lifetimes go down quite fast. So this is something that has been calculated actually with EPW, and that probably you would see today and tomorrow. So that's basically the end. I'm sorry for being late. I guess the message I try to convey is that a quantum field theory is painful, but once you go over the hill, it's amazing. You can really describe a lot of interesting physics, and that's really a very fundamental way to proceed. And that's actually also a way to understand how to improve over DFT calculations in a systematic way, okay? So I didn't discuss other details, but with this, you can also understand why, for example, certain functions do better than others and many other details. So we will not have time to go through that, but I hope that you got an idea that we can discuss electron-phonon physics using a very, very, very clear and mathematically robust formalism. We don't need to invent approximations as we go, okay? So this is all very systematic, all right? So that's the end of it. If you want to look at the equations, basically I squeeze all the equations I gave you today are in this review paper, but if you want to look at something more advanced, there are all the other reviews. In particular, if you have not ever seen a quantum field theory, but you're interested in it, so this book is fantastic because it really gives you all the derivations. So it's very old, but it gives you all the derivations, all the steps, and it explains why we do certain choices. So that's a good starting point if you're interested, all right? So that's the end of the lecture. So